You can define xi, again, find as binary variables. If project number 2 has to be done, then x2 equals 1, right? If you say exactly two of the three projects, two of the four projects, project 1, 3, 5, 6 must be done, only two of them, right? Then we can certainly write x1 plus x3 plus x5 plus x6 equals 2. If projects 3 and 5 must be done at the same time, so how do we write this one? All right, I'll start with you.
Maybe x3 equals x5?
Yes, do you agree?
I was going to say modulus x3 equals x5, so modulus 2 equals 0.
Module?
Yeah, so it's the remainder of the division.
Remainder of the division, but that's not a linear constraint.
Okay.
Can be done, yes. Okay, so we can simply write x3 equals x5. If we say projects 1 and or 4, but not both, must be done, this is very similar to here, right? So then it's x1 plus x4 has to be 1. If we say project 4 requires project 1 and project 3 to be done, that's like only if constraint, right? You can do project 4 only if project 1 and project 3 have been finished, right? So again, this probably is not that clear, but it means it's an only if constraint. So as we said, you can write 2x4 less than equal to x1 plus x3, or you can write this x4 has to be less than equal to x1 and x4 less than equal to x3. So here says if projects 1 and 3 are done, then project 4 must be done. So this is like a if-then relationship. If, then project 4 must be done, right? So do we have this equation here? I think we have. That's something here, right? So here you can write x4 is larger than like this. So x4 larger than equal to x1 plus x3 minus 1. Any questions? So in this slide, we are talking about, how do you know if the constraint you write is correct? Yes.
Question. So for number 6, you know how for number 5 we have the two constraints?
Yes.
Can we also do like for number 6? Can we also do x4 has to be equal to x1 and x4 has to be equal to x3 to make sure that they're both done?
You mean larger than equal to, right?
Like equal to.
We can write x4 equals x1 and x4 equal x3.
Yeah.
But what if x1 is 1 and x3 is 0?
Then x3, then x4 is 0.
But has to be equal to 1 because x1 is 1.
Okay, so let me write it down and see. That's a very good point.
Sorry, greater than or equal to.
Yeah, that might be better, but let's see. Wrong out of space. Control right here. Okay, so certainly you can write x4 larger than equal to x1 and x4 larger than equal to x3. Then, if this is down, then this must be down. If this is down, this must be down too.
But if they're both not done,
Yeah.
export could still be done.
Yes. So if this is 0, right? If project 1 is not done, then this is okay. But if what I'm saying is that you have 2 projects, 1 and 3, right?
Yeah.
If you only have 1 project to get done, if x3 equals 1, for example, if project 3 is done, that means x3 equals 1, the x4 has to be 1 too, right? Has to be 1. So you kind of capture what we want here, but not exactly,
Right.
because you make this a little bit more restrictive. You are saying that if any one of the project 1 and project 3 is down, then project 4 has to be done as well.
Okay.
So I think this is better. So it is quite, so just in case, I probably want to erase it. I think the solutions are okay, probably this is better. Now, if you think about it, right, we are talking about 3 projects, right? And if you have, say, 10 projects, okay, then you say that your projects 1, 3, 5, 7 are down, project 6 must be down, then it's more complicated, as you can tell. But as the number of potential decision variables grow, the problem will become more difficult. Okay, so here just saying that you write these constraints and you like them, but how do you know you get what you want? Especially something not as intuitive, right? So one way to make sure this is what you want is to just check all the combinations, because x1, xi, any value can only take 0 or 1, right? So for a very simple example, suppose you want to check if this x1 plus x4 equals 1 is what you want for this here, you just write all the possibilities, right? If x1 is 0, 0, or 1, if x4 can be 0, can be 1. And then you can see if the left-hand side equals right-hand side. You want to see if they match, right? If they match, that's what you want. So this is a way to check if your constraints are correct or not. Okay, so you write, binary program, how do we say it? Binary programs, or you have integer programs, right? How do you solve them? How do you solve them? And when you solve them, what are the possible situations? So if you remember from, linear programming, we said that for a linear programming problem, you may have those situations, right? You may have a unique optimal solution. You may have alternate optimal solutions. That is, you have infinite number of optimal solutions. You may have an unbounded problem. You may have an infeasible problem, right? Of course, unbounded problem and infeasible problems are more likely to happen if your program formulation is incorrect. Okay? But this is the same case for integer programming. If you run an integer programming, you may have a unique optimal solution. You may have more than one optimal solutions. So also possible. Of course, if your integer programming formulation is not the best, you may have a bounded problem, you may have an infeasible problem. Now, how do you solve it using Excel solver? Very similar, right? Just only one thing is different, which is you have to force or kind of specify the type of decision variables you like. Okay, if you want to force say x2 a binary, right? If you want to have binary variable in the solver, you can select bin as the type of the variable, which is the binary variable. If you want a certain variable to be integers, again in the diagram, you can select integer int, which stands for integers. Okay. And the YouTube video tells you about how to do that in Excel solver. But again, it's very similar to what we did before. Now here's the good news and the bad news, which is you're using solver, you can do you can also have the sensitivity analysis reports, right? Those reports are not useful at all for integer programming models or for mixed integer programming problems. Okay, so basically those sensitivity analysis, they assume that all the decision variables are continuous. That means if you have to have an integer decision variable in your model, then sensitivity analysis reports from Excel solver are useless. Okay, so this is a good news because you don't have to worry about sensitivity analysis reports for integer programs. Okay, so next I want to talk about some mixed integer programs. Okay, mixed integer programs. The first one is called fixed charge problems. Again, probably take 1 minute to check out what we have here. So how do we formulate this situation? All right, so this is a transportation problem, right? But it's different because you have to decide whether to use a source or not. In this case, whether to use a warehouse or not. So if you lease the warehouse, you're going to get capacity, but then you have to pay a fixed charge, like a rent, rental stuff, right? So you want to decide which sets of warehouses to lease to meet the demands. Okay. So to list or not, this is a binary decision. So we can define xij as the quantity to ship as usual. And now we have a binary variable. We have binary variables yi, which is if you list warehouse I, you will have yi equals 1. If you don't list warehouse I, yi will be 0, right? And you want to minimize the cost of transportation and also leasing, right? So this term, as we know, is is to use notation to write the transportation cost, right? But then we also have leasing cost, right? So here says, if yi equals 1, then you have to pay fy, right? I mean, for example, if you are talking about the warehouse 1, right? If you lease warehouse 1, then y1 equals 1, then you have a fixed cost, f1, right? If you do not lease warehouse 1, then this is 0, and this becomes 0. So of course, if you don't lease warehouse 1, there will be no leasing cost, right? So by doing this, you kind of capture that situation. So remember, yi is a decision variables, right? So the system is going to run the program and see which, whether it's optimal to have yi equals 1 or have yi equals 0, right? So that in itself is a decision variables. And about constraints, again, for the demand side, everything is normal. But for the supply side, we have something special, which is if you do not lease warehouse 1, then of course you do not have capacity at warehouse 1, right? So on the right hand side, if you do not lease warehouse 1, then this is 0, then U1, whatever it is, the whole thing will become 0, right? If you lease warehouse 2, then this is 1, the U2, this becomes U2, right? That means if you lease warehouse 2, then you have U2 as the capacity. And that's what we want, okay? So everything is the same except we have used binary variables to model the fixed charge, the fixed leasing cost, or we have used binary variables to model the capacity, the fixed capacity. So the capacity can be 0 or can be whatever you have here, right? So does it make sense? Any questions? Okay, if you don't, we have another question here. So this one probably is a little bit more involved. So let's, how about you guys take 2 minutes to try this problem by yourself. yes, we want to formulate the program to. All right. So you want to produce some kind of food, and which requires the refining of oils, right? You have 2 types of vegetable oils, 3 types of non-vegetable oils. Not that it's important here for this problem. They have the prices for each oil, right? And you make the product, if the price is 180, and you have different requirements about different constraints about those oils. You cannot refine more than 210 tons of any vegetable oil, and you cannot refine more than 260 tons of any non-vegetable oils. Okay, what else? So you also have to make sure the hardness of the food is enough, right? So the hardness have to be 3.5, between 3.5 and 6.2. Okay, and those are the, I don't know what we mean by hardness here, but for each type of oil, there's a hardness characteristics. Okay. You want to maximize profit, and you have more constraints here. The food may never be made up of more than 3 raw oils, and if oil is used, at least 30 tons of that oil must be used. Okay. Okay. So if any type of oil you use, you have to use at least 30 tons, and then you have this constraint: if either vegetable 1 or vegetable 2 are used, then oil 2 must be used. Okay, so as you can tell, the question is whether to use it or not, right? And how much to use. So those kind of questions, whether to use or not, that would be binary. How much of it to use, that's like continuous, right? So this is like a mixed integer program. So we can, again, it's kind of backwards, but we can define xi as the amount of oil to use okay, let me change to cocoa. And you can also define yi as a binary variable. That means if you use oil I, then you make this 1. If you don't use oil I, then you make yi equal 0. Okay, so the first constraint says you cannot refine more than a certain amount of oil. So here says what? You cannot let me see. You cannot refine more than 210 tons of any vegetable oil. So this is a little bit, not as clear. Let's say we assume that we cannot use more than 210 tons of vegetable oil combined. We cannot use 260 tons of non-vegetable oils combined. Then we can have this constraint, right? Because x1, x2 are the. Okay, where is it? Yeah, so if I equals 1, that means veg 1, I equals 2 means veg 2, I equals 3 means is the oil 1, the non-vegetable oil 1, and so on, right? So that is that. Now, the hardness of the final product must lie between 3.5 and 6.2. This is like the average, right? Average hardness has to be more than 3.5. Right? Again, x1, x2, those are the amount of oils you're going to use. Those are continuous, and we assume that the hardness can be measured. It's like a linear, it's like a linear combination of all the oils, all the components you use, right? So if you use x1 pounds of veggie 1, then 8.8 times that's like the total hardness from veggie 1, right? If you use x2 times of veggie 2, then 6.2 times that means it's almost like the total hardness from veggie 2. So here, the term is the total, right? The total like hardness divided by the total pounds of oils you use, right? X1 plus X5. So this is basically the average hardness of the final product. Has to be at least 3.5. Now, this is good, but it's not what we need in the end, okay? As we said, in linear programming, in integer programming, what we want is linear constraints, okay? So you have to convert this into, you have to simplify it into something linear, okay? You cannot just leave it that way, but I mean, from here to a linear constraint, so I'm pretty sure you can do it, right? Okay, what else? So mass relates to amount of used to integer variables, okay? Because you don't, whether you use or not is not a sure thing. Whether you use oil 1 or oil 2 or not is not a sure thing, right? If you don't use it, then you don't xi has to be 0. Okay? But if you decide to use oil 1, then you cannot use more than 210 tons. Okay? So this is what we have seen in the transportation problem. On the right hand side, you have the fixed, like the number times the yi, which is a binary variable. Okay? So the food can never be made more than 3 raw oils. That's that, right? No more than 3. If any oil is used, at least 50 tons of it have to be used. Okay, so probably for economy of scale or something, right? So xi has to be 30 times y. If it's 0, if you don't use y, of course, this constraint is redundant. Okay. So the last one says if either veggie 1 or veggie 2 are used, then oil 2 must be used. Oil 2, the corresponding variable is y4, right? And this is y1, this is y2. And that's actually exactly what we have in the previous example, right? So if y1, y2, either one of them is 1, then y4 will be 1, okay? Because y4 is always larger than equal to y1. Okay, so I guess what we are trying to say is that you can use binary variables and model quite a lot of situations, right? And then you have the objective functions. In this case, the objective function is relatively easy to do. It's like blend problem. You mix x1 pounds of oil 1, you mix x2 pounds of oil 2, then the total product, the total weight of the final product is x1 plus x2, right? The typical blend problem. So that is the selling, that's the revenue minus the cost, right? So this is relatively easy. Any questions here? Okay, now I want you to take out a sheet of paper and solve those 5.